Hello everyone, in this video we'll be solving problem 45 jump game 2. The problem statement is we are given a zero indexed array of integers nums and length n where each element nums of I represents the maximum length forward we can take a jump from index I. We need to return the minimum number of jumps to reach the last element in the array, that is n minus 1. The inputs that will be given to us are sure to have a path to reach from the first element to the last element. In example number 1, with this as our input, we need a minimum of 2 jumps to reach from the first index to the last index. This problem is very similar to problem number 55 jump game. The only difference is in that problem we had to figure out if we can reach to the last element from the first element, but here we need to figure out the minimum jumps that we need to take to reach to the last point. Because the problem statement is quite similar, we can use similar approach to solve as well. So let's switch to whiteboard and discuss the solution, starting with the brute force approach, and we'll slowly work our way towards improving the solution. Because we need to figure out the minimum number of jumps, we need to try all possible combinations to reach the last element in the array. In the brute force approach, we'll try to build a tree or a graph that will highlight all of the possible combinations we can build at each node or each element and see which one takes us to the last element efficiently. Starting with the first element 2, we have two options. One is to make a jump of one space and the other is of two spaces. If we go with one space, the next element on the left hand side will be 3 and 1 on the right hand side. Now at node 3, we have three options. One is to make one space jump, two spaces or three spaces. And each of it will take us to a different element. One will take us to 1, the other will be taking us to 1 as well because there are two ones in the input, and jumping 3 spaces will take us to 4, which is the last element in the input array. If we look at the path starting from the first node 2 to 3 and to 4, it took a total of 2 jumps to reach to the last element. Similarly, we'll try to run through all the combinations on all of the other elements to see if we can get a better answer than 2. With this solution, our time complexity is O of n square as we are going through multiple combinations to identify which can get us the minimum jumps to reach the target. While the space complexity is O of 1 as we are only using one variable to record the total number of jumps needed to reach the target. If you pay close attention to the approach that we just discussed, there were few nodes whose calculations were being repeated in multiple legs. For example, node 1 was being repeated multiple times as part of the leg from 2 and as part of the leg from 2 then 3. If we extend this tree, we'll find more examples where the number of calculations are duplicate. One way to optimize this is to implement dynamic programming into the solution where we can use an array to record all of the nodes or elements that have been visited. The dynamic programming array will be of size n, and before processing any node, we'll first do a lookup to check if the node has already been processed. If yes, then we'll take the value from the array instead of processing or running the calculation again. With this change, our time complexity is improved to O of n as we are only processing each node once, but the space complexity is increased. The new space complexity will be O of n because we are using this dynamic programming array to keep tabs on all of the elements that we have visited. I hope you were able to follow the two approaches that we just discussed to solve the problem. Now let's discuss the third approach, which is the greedy algorithm, which gives us the best of time complexity and space complexity. In the greedy algorithm, instead of just trying to figure out the minimum steps that we need to reach to the last element of the array, we'll try to calculate the minimum spaces or jumps needed to reach to each element in the array and build on top of it. And for our understanding, we'll group all of these elements in the array based on the minimum jumps that we need to reach there. Let's simulate it with an example. With no jumps, we are at position 0, that is the value is 2. From index 0, we can make two jumps. One is to get to position 1 and the other is to position 2, that is 3 and 1. In other words, we need a minimum of one jump to reach to elements 1 and 3. Now for the next jump from 3, we have 3 options. We can either make a jump of 1 space, 2 space or 3 space. Node 1 that we can get with jump 2 is already covered in jump 1. If we can get to node 1 with just a single jump, why would we want to get to node 1 with jump 2 starting with 2 to 3 and then 1? It is inefficient, so we'll not include it for jump 2. Repeating the same process for node 1 at jump 1, we only have one option. We can make only a jump of 1 space, so the next element is 2. As 2 is already included for jump 2 level, there's no point in adding it again, so we'll just skip it. As we were able to get to the last element 4 with the second jump, the output is 2. Let me update the input array so that we can do one more run. We have 2 elements that we reach after making 2 jumps. Now for the third jump, we can make from node 2, which will take us to either 4 or 1. Similarly, we can get to the last element from node 4 as well by making a jump of 1 space. So with this input, we were able to get to the last element with just 3 jumps. There's one oversight here. Node 4 should not appear in jump 3 because it is already covered in jump 2. If we can get to node 4 with 2 jumps, there's no point in keeping it for jump 3. So I'll take it away. So there's only one element 1 which can be reached with 3 jumps. With this solution, our time complexity is O of n, as we are running a single loop to iterate through all of the elements 1 without running any nested loops. And the space complexity is O of 1, that is constant space, because we are only using couple of variables to point at the current element and maintain the range of the current jump. I hope you were able to understand the explanation on how we use greedy algorithm to solve this problem. Let me show you how we can implement this using Java. Here's the solution in Java. In the main method, I have added a basic validation to make sure that the length of the input array is always greater than 1. After that, I have initialized in 3 variables. The first is to record the total number of jumps needed, the current end, which will be the boundary of the current jump, and the index where we land with the current jump. Post that, I am starting a for loop to iterate through all of the elements in the input array. Within the for loop, I am calculating the farthest we can go with the current jump by comparing the previous farthest calculated with the current jump, and whichever is higher will be saved back into the farthest variable. After that, I am checking if I is pointing at the boundary of the current jump. If yes, then we need to increment the jump by 1 so that we can start a new jump and update the current end to farthest. After the for loop is complete, we return jumps as our output. This code, when submitted on LeetCode, beats 99% of the submissions in terms of runtime and nearly 86% in terms of memory. Thank you for watching this video. I hope you were able to understand the explanation. The details to access the source code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.